Let's start with this. Then we're going to jump to the DFS, BFS. When you get used to the DFS, DFS, and then Dijkstra, it'll be actually much easier on you. Just in the beginning, it's a bit confusing, but after that, it's going to be easy. I'm sure the same way if you think about the time complexity, the big O, when we've learned it in the beginning, when you're seeing algorithm, it used to be harder for you to deduce. Now right away, you look at it, loops, log of n, it's much easier for you now, right? So the same thing will happen with the graphs, so don't worry about it. Everyone, and let's start. What is a spanning tree? Again, think before answering, guys. Think before answering. So dissect spanning and tree. What is a tree? Then what is spanning? And then you'll be able to figure it out. Again, guys, cycle 3. Cycle 3, always, okay? That means spanning tree when all nodes are visited, but there is no cycle. Trees are always related to cycles. And depth first search, we use what? Stack or a queue? Stack or queue? I want you by at this point, I don't want you to confuse these two. Stack all the time. Why? Depth first search. So what is going to be last in, first out? Is it possible to find the shortest path using depth first search? Shortest path. It's no. Why? Because if you're going from, let's say, A is connected to B and C and D, and you want to go to D, no, because it's depth first search, you're going to go from A to B and then continue from B until you arrive to D. So if you look at the graph, it's going to be very obvious. So of course not. What is the big O of incident edges function? Remember, what is incident edges function? That means if I'm giving you this node V, and I want to know all the edges connected to V, I have an adjacency list and adjacency matrix. What did we say? How do we represent the matrix? N by N, correct? And then the adjacency list is what? I only have N nodes, and each node only is connected to what? Only the edges that are connected to it. These are very important, guys. The first one, 100%. So the adjacency list, you have each node, you know where it goes. Like, for example, node B, right away, you're at B, and only the degree of node B is saved. And then for the adjacency matrix, you have to go through all that. Now, BFS uses what? Q, of course. Both DFS and BFS runs in O n plus m. Is this true or no? Or is it only the DFS? You remember? Actually, always remember, BFS and DFS are the same time complexity. The only difference is that BFS, you're able to find the shortest path. DFS, you can't. But both are run by n plus m, which is, O n plus m is what technically? How can I write it? O of m, okay? Now, can the worst time complexity of DFS or BFS be O of n squared? Is it this possible? I know nothing is impossible with you guys, but is this, what about this one? Yeah. Very good. So of course, yes. Why? Because as, what's your name again? Habiba said, when the what, 1 or 2. So if you didn't hear what she said, which one? In which case is going to be O of n square? Actually, it's true when we have the maximum number of edges. But what is the relation between maximum number of edges and n square? What's the relation? How did we know? Did we just memorize this? What is the logic? So in the exam, if you're, let's say, having anxiety and you cannot remember anything and you want to just do it yourself on a paper without memorizing. So what's going to happen, Riley? How can you connect it?
You have the maximum number of edges. One node will be connected to every single other node. That node has n edges, but there's n nodes, so there's n edges n times, which is n times n, which is
Okay, but that's not like, that's correct if you want to think like that. But the proper way that we have seen in the slides is what we want to get. So this is O of m, right? M is the number of edges. That's why it's connected to the number of edges, because O of m is the number of edges. It's connected to the number of edges. Now, what did we learn? We learned that when we have a complete graph, as Riley said, we're going to have the maximum, which is the summation of the degree, blah, 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 but it's going to be n squared. But remember always, why it's connected? Because it's O of m. M is the number of edges. So everything is going to depend on the number of edges. The same way in the binary search tree, it's O of h. So that means it's going to depend on the height. Here, O of m, so it's going to depend on the m, which is the number of edges. Which algorithm is more suitable if I want to find the shortest path? Of course, 100%, it's the BFS. Can I calculate the shortest path using breadth first search? If the edges have different weights, we said you're not going to know this now. Nope. So you're going to use Dijks. Now, if I have a complete graph, which is the same as maximum number of edges, it's called complete graph. And I'm using adjacency list data structure to represent this graph. What is the time complexity to running a DFS? It's a new question. That's the first time I'm asking you this in this, right? I want everyone to answer. We have only 40, 76 logged in. So let's have everything, everyone answering this. More people. We have log of n, that's of course random, and log of n random. So it's O of n or O of n squared. Is this the new question that I just asked? Or is this the same question as this one? The same exact question, but this one is theoretical. This one is more like articulated in a time complexity one. So what are we saying here? Let's look at this. If I have a complete graph, maximum number of edges, that means I know that m in this case is going to be what? N squared. We already answered this. And a complete graph, m is equal to n squared. Now I'm saying I'm using adjacency list data structure. In the adjacency list here that we just answered this question, you said that adjacency list take degree of v. That means take the summation of degree of v, which is 2m or m. That means an adjacency list, what? It depends on m. And because it's a complete graph, it's n squared. So what is the time complexity of n squared? Now, what about the case of BFS? N squared, because again, BFS and DFS, both of them are O of M. Okay, so if you get something like this in the exam, don't say, oh, we've never seen this in class, because we just changed the wording. You need to understand what you're answering before just like, don't memorize words, okay? Understand, and then you'll be able to answer it. So of course, O of N squared. Very good, okay? So now we're going to jump from theory to just like solving questions that it will help you also understand how to solve the assignment and also for the final. Now, before we start, I received a question after Tuesday. A couple of you came and asked me a question. What is this question? Do you remember when we said what was the problem with the algorithm of the DFS and BFS? Because we're going to have a problem if we're just using an algorithm like this and we're passing only the node V. We said, what is the problem in this case? Habiba. Exactly. We said, what if the graph is like this? We said there is a problem. So what do I need? How can I fix this? I have to create a bigger function that takes a graph. Okay, so it takes the graph as the input, and then inside it, it's going to call another function, which is going to say, okay, when you're looping through the graphs nodes, for example, here you're going to input the actual node. So the question that I received, how can we input a graph into this? Okay, the way you want to think about it, guys, this is what you're visualizing here. Correct? That's non-connected graph. But how do we implement and which data structure? Let's say I'm using adjacency list to implement this graph. How can I do that? Technically, and I'm saying this is A, this is B, this is C, this is D, this is E. Okay? And this here is 1, 2, 3, and then 4. These are the edges, the number of edges. Let's say this. I have here A, B, C, D, E. And then here, what do I have? The edges, which can be like A, B, or 1, or whatever. So this is the graph. It's represented like this. There's an array that has the nodes in it. So when you're feeding the graph, you're feeding this. So I can go through this. You're not feeding this image from that it's unconnected, right? So you're feeding this actual data structure. So these A, B, C, D nodes inside the array, they all exist. But how do we know that they are non-connected? It's like this. So we have A, B, C here. Sorry, A, B, and then you have A, C, and the B. What do you have, guys? BA and BC, correct? And then for the C, what do you have? DA, D, B. For the D, what do you have? DE only. And then here you have, from these, that's how the program knows that they are not connected. But actually inside the array, all the nodes are available. So when you're feeding a graph, you're feeding this. Okay, so that's what's happening behind this. Now, this question is very good. That's why I encourage usually if you want to ask it during the lecture, that's fine. Also, everyone will benefit. So, few things that you actually need to focus with me because they are going to either give you a correct answer in the exam or a wrong answer. If you don't know how to read this question, you may have a problem answering. Why? Because when you want to use the stack, depends on what am I telling you, how am I telling you to use it, it's going to end up a different answer. So let's see. Perform a depth first search traversal algorithm on this graph starting from node 2. I need to give you the node because this is not a tree. So I don't have a root that I have to always start. I know this is the root. I always start from the root. Here, if I give you this, I need to tell you from where to start. Okay, so that's the first point that we know. So node 2, I need to start from node 2. Using a stack, when you push the edges, so this is the most important thing, when you push the edges of node in the stack, always follow the adjacency list order. I'm telling you how to move, because you cannot answer, like, for example, you have 2, 1, 2, 3, 2, 6. Which one is going to be answered first in the stack? Depend on this, you're going to have a different output. So you have to follow the question. The question is telling you here, always follow the adjacency list order for node 6, for example. Edge is going to be 6, 2, 6, 3. So whatever you have here inside this, you're going to input into the stack. So let's see. In the beginning, we may ask you, do the adjacency list based on this graph. So how are you going to do this? So 1, how do you fill it? Who wants to do it?
1, 2,
So it's going to be 1, 2,
3, 1,
1, 4, right? And then for the 2, going to be what? 2, 1, 2, 3, 2, 6. Easy. When it comes to the adjacency list, you just input them like this. Now, why we're putting 1, 2, and 2, 1? Again, because this, it seems like undirected graph. So you put them twice, one as 1, 2, and the second as 2, 1, but they are the same. So this and this are the same. Even if one says 1, 2, the other one 2, 1, they are the same. Okay? So let's go right away. Forget about this for now. This is how it looks. That means now, if you're starting from 2 and you want to follow the adjacency list order. So I go here, that's 2. What do I need to input or to insert first in the stack to push first? It's going to always be 2, 1. So 2, 1 first, 2, 3, and then 2, 6. This is important, guys. Okay, I'll tell you why it's important in a bit. So let's start. So the first step that you're always going to do is you want to put here the visited nodes, and then you will have discovered edge and back edge, correct? What do you mean? Who can remind me of what is the back edge? You want to? I didn't hear you. Not cycle, no. Technically, yes, when you have a cycle, true. Yes, that's a correct answer. So technically, you already visited B, and you're at C. If you want to go to B, it's already visited. So that's a back edge. Why? Because if you continue it, it's going to have a cycle. So now, the first step, I chose 2. I put 2, 1, 2, 3, 2, 6. What is the next step? It's a stack. So this is the top of the stack. I have to pop. So if I'm taking 2, 6 out, what are the steps that I need to do all the time? First, exactly. So the first thing, I'm going to do this myself, and then I'll let you do them. First, I'm going to add 6 here, because 6 is not visited, correct? So that's 2, 6. And then what also? I have to put the edge, because the edge is not visited. So technically, it's going to be like this. So that's what happened. So first step, second step. Now, what is the third step? If you don't do it, that's not depth first search. The third step is that you put 6, you're here, you have to now what? Push the edges of 6 inside the stack. So how do you do them? You're going to follow the adjacency list. So you go here. I have 6, 2, 6, 3, 6, 4. Now 6, 2, I'm not going to put it because it's already visited. So I'm going to put 6, 3, and then 6, 4. Good so far? So these are the 3 steps that I need to always do. Now, let's do it together. And guys, trust me, even if you're super tired, even if whatever, it's only 40 minutes. You focus here, it saves you 4 or 5 hours of studying at home to try to remember what are the steps for the DFS. 40 minutes, and then it's easy. So what is the next step? Fida, do the next step.
Pop 6, 4.
Okay, it's a stack, so I need to pop 6, 4. Okay, when I pop, what do I need to do?
Check it. We put 4.
Very good. So I'm going to put 4 here. 6, 4. So I'm going to look at the 4. 4 is here. What is the next second step?
Then we go and we will put in the stack the edges of
Before that, there's a second step. You have to also put 6, 4 in the discovered edges. Correct? So first step, I put 4 as nodes, 6, 4 as the discovered edges. And then I'm going to do the third step, which is I'm going to go to 4 here. And I have to push these 4, 1, 4, 5, 4, 6. Which one you're going to push?
4, 1, 4, 4, 5, and 4, 6, no, because we are already.
4, 1, 4, 5, 4, 6, no, because we already have it visited. So it needs to always, if it's here or here, you don't put it in the stack. So very good. So 4, 5, and then 4, 6. Now, I want someone who's still not sure about it, he wants to try it.
You said not to put the 4, 6.
Why? Sorry, my bad. Very good. That means you're awake. Very good. We have 4, 1, and 4, 5. Very good. So now, who wants to do it? Yes.
Up 4, 5.
Exactly. So again, guys, there's no need to be confused. What are the next step? You're using a stack. What do you do in the stack? You can only push or pop. So you're going to pop. Okay. 4, 5. So what do we do?
Put it.
Is there any 5s here? And then visited? No. So I'm going to put 5. What else? So that's 5 here.
And put it in discovered edges.
And 4, 5. What's the third step?
All the.
I go here. What are the addresses that I need to write? Which is 5, 4. Do I have 5, 4 here or 4, 5? Yes, you can see it also. It's also visually good to do it on the paper, so you don't have to put anything. Very good. Thank you. Yes. No, there's no back edge here. Back edge is, we're going to see it. What's the next step? Again, someone's not very confident about it. Wants to try it. Everyone A+, very good. Who wants to do the next step? 4, 1. Manuel.
4, 1. And
So do you see here, we didn't push anything, but we have it stacked. We continue. We don't just leave it, lock the door, and go home. We continue. 4, 1.
there you put the 1 down on your list.
Yes.
And then you put your discovered edges for 4, 1. Then you go through 1 and put down everything except 1.
I go here. That's 1. So what do I need to put?
1, 2.
1, 2, 1, 3. Do I put 1, 4? Or is no need?
2, 1. We want the 1 for POE use there.
No, that's different. Do you see? So you want to look here. That's very good, guys. So look, when you're putting these, you're not looking at the nodes. You're looking at the edges. 1, 2. Do I have 1, 2 in the discovered or the back edge? No. Do I have 1, 3 in the discovered and the back edge? No. Do I have 1, 4 in the discovered or back edge? You may think no, but technically yes. 1, 4, 4, 1 are the same edge. So 1, 4 and 4, 1 are the same edge. So because I have it here, I don't put it. So it's not based on the node. It's based on the edges. Very good. So I have these. Okay, what's next? I want someone from this side. Look. One, 3. Okay, so what's next? So you put 1, 3. So that means you're 1 and this is 3. Correct? Is the 3 here visited? Okay, so what are you going to do? 3. What else? So how are you going to come here? Parachute, or you have to go there, traverse? So you have it to visit. So that's also what? 1, 3. What's the next step? Three steps. First step, you want to put if visited. Second step, you want to put the edges. The third step, this 3, you go and check what edges that have, so you can push it in the stack. So you have 3, 1, 3, 2, 3, 6. Which one you're going to push? 3, 1. Okay. Do you have 3, 1 here in the edges? Okay, so I'm not going to push. 3, 2. Do you have it? There's no 3, 2 here. So what's going to happen in this case?
I mean,
It's okay because we didn't cover this, so don't be scared. It's okay. So 3, 2. What's going to happen with the 3, 2? 2 is visited, so I don't want to push it, but it's not here. So what can I do? I'll put it here. Or you can push it here, and then when you pop it, you can say, okay, it's going to be in the back edge. It's okay. Both of them are fine. But technically, this is the back edge now. Yes, Milan.
Just one question. When we went to, when we were at 4.
Mm.
I think it was 5. The one on the right.
Yes, 4, 5.
Went back to 1.
Yes.
It's not a cycle, but like, don't we have to go back to 4 to go back to 1, technically?
That's the thing, because you're implementing it based on what? On the stack. So you're following whatever in the stack. We didn't. So after 4, 5, under it, we had 4, 1. So that's why we followed 4, 1. Okay, I'm going, and there is animations. I'll check the animation for you. So look. So look at here. That's 4, 5. That's 4, 1. You're here, correct? So you're at 4. And this is 4, 5, 4, 1. You took 4, 5 out. What's going to happen? I took 4, 5 out. I'm here. I don't have anything to push. What's next in line? 4, 1. Correct? So I'm going to go now and visit 4, 1. These are edges, not nodes. These are edges inside the stack. So that means go to this edge called 4, 1.
It's not like we're visiting the node again.
No. In the algorithm, you're going to see when you call 4, 1, there is the opposite. So you remember, if you look at the algorithm, you're going to see, okay, what is the opposite? So you're going to say node, opposite of 4, 1. That means the opposite is going to be 1. So there, but here, the idea of stack, if you know that you're going to pop from the top, 4, 5, 4, 5 is done. What's next? 4, 1. You just follow the order of the stack. That's it. Okay, that's why a stack is super easy. Now, when you get used to it, you're going to look at this, and believe me, at some point, I don't want to waste my time and do the stack. You're going to look at the graph and just do it right away. When you get used to the depth first search, it's easy. If you have not a very complicated graph, it's very easy. Like we can do this one here without even stack. But the stack will tell you how this is done step by step. So whenever you're confused, like for example, now you had a question in your mind, do I need to do this? And the stack, you don't have to question yourself. There is a specific steps instruction that you have to follow. 4, 5, what's next instruction? 4, 1. 4, 1 is done. You follow these instructions. That's it.
Sorry, I missed that. How'd you get the back edge again?
Oh, so the back edge, we're going to go for it again. So let's go here. We are 1, 3, correct? We are at 1, 3. And let's delete this also. Now I'm 1, 3. So let's do it together, Bas. So you're going to pop.
Use the stack.
Okay, so you're going to pop 1, 3. What's going to happen? I'm going to add 3 here. And then I want to add 1, 3 where? Here. What's the next step? I'm going to go to 3. For 3, you have 3, 1, 3, 2, 3, 6. 3, 1 is here. I'm not going to do anything about it. Now, 3, 2. For 3, 2, you have to go and search the edges. Do I have any 2, 3, or 3, 2 in the edges? No, I don't have. That means I need to put this 3, 2, right? The 3, 2, I need to put the 3, 2 either in the discover edge or in the back edge. I need to put it somewhere, right? It's an edge. How can I decide based on what? If the 2 is visited, I'm going to put it in the back edge. If it's not visited, it's a discovery edge. Do you see the steps, guys? So in this case, 3, 2. So that means here, if I go here, I'm going to have it in orange. Now, 1, 2. What's the next thing is 1, 2. I want to pop 1, 2. I pop 1, 2. 2 is already visited. Yes.
I still don't understand why we didn't put 3, 2 in the stack instead of the back edges.
Okay, so let's do it. So we have 1, 3. One, 3, correct? 3, 1, we're not going to touch it. 3, 2, I'm going to put I'm going to put 3, 2, and then I'm going to put 3, 6. I'm going to put them both. Okay. Let's do 3, 6. What's going to happen? I popped 3, 6. Is 6 here visited? Yes. So I'm not going to put 6 here. Now I need to put 3, 6, this edge here. I need to put it somewhere. It's either here or here. How can I decide that? If this one is already visited, I'm going to put it in the back edge. Okay, so where I'm going to put 3, 6? Here. This is done. Now 3, 2. Again, I'm popping 3, 2. Is 2 exist here? Do I have 2, 3 or 3, 2 in the edges? No, I don't have it yet. So if you look here, in the orange, we have this. But then this one here, there's no color of it. So that means I didn't put it here. If you look here, there's no, it's not here, it's not here. So I need to decide, should I put it in the discovery edge or in the back edge? If 2 is visited, it's going to go to the back edge. So that's 3, 2. So you can put them in the stack. If you want to do it step by step, continue doing. But I'm saying at some point you're going to know them like this. You don't have to put them. But technically, if you put them, it will have the same exact. So let's continue and put everything just for us to not miss any steps. So in this case, what is the next thing? Everything here is what? So this is here also 3, 2 like this. I have to go to the 2, 3 in the stack. Yes.
After the 2, 3, 2, then the next one will be 1, 2.
Oh, I crossed it out. Okay, okay. Yeah, when we were talking. Very good. So 1, 2. So I'm at 1, 2. What do I need to do? Who wants to do it? Just this is the back edge. If you're still confused about the back edge, do it.
You pop it, and then afterwards you look in the visited nodes. You can see that like it's already there, so you know that you can put it in the back edges.
That's, oh my God. Okay, so 1, 2, and then I pop it. I put 2 is already here. Where I'm going to put the 1, 2?
In the back edges.
Okay, very good. So if I want to go now and see in a clear way, so these are the animation here. So let's go at the end. So now we start putting the 3, 6 here, 3, 2. Now 1, 2, what's going to happen? Also the 1, 2 is going to be here. And then all of these are going to be popped. There's no reason to put them. Yes, Ant.
I don't understand why we blocked the back edge array. Like, what did it help us to do in the algorithm?
Which one?
The back edges.
The back edges, you need them. Why? Because if you want to find a cycle, because technically the DFS, one of the main uses of the DFS is to find if there is a spanning tree or not. So what is the spanning tree? There is no cycles. So if your back edges is empty, that means you don't have a spanning tree.
The way I'd implement it is just check every time I get to a node if it's already in the visited node and there's no need to waste space for the back edges, right?
From the way you implemented in the algorithm, you can do, like, I think in the lab, you've done something. But here, the way that why we're putting this, because in the exam we tell you, I want you to know if you know what are the back edges. This is not like an implementation in the memory or anything. This is just for me, when you submit the exam, to know that you know what are the back edges. Yeah. Okay. So who's still confused? Yes.
Matter. You have to set it's like should be 3, 6, 3, 2, and 1, 2 for the back edges, right?
No, these order doesn't matter.
Oh,
So the back edges, it's okay, it doesn't matter for the back edges. Now, why did I say, guys, the edges of the nodes, the way that you're putting things in the stack is very important. Look what happened here. If I'm following, the discovered edge are important. So what's his name? Edward. So the back edges maybe here doesn't matter for us too much, but for the discovered edge, it matters. Why? Because if I'm telling you, draw me the path based on the discovered edges, what are you going to say? I was here, so I visited 6 first. Then from 6, I went to 4. So these are important. And then from 4, I went to 5, blah, blah, blah. Now, look at this, guys. If in the exam or the assignment, I tell you, I want you to visit, to try use DFS and visit them based on the order. Or the like 1, 2, 3, 4. For example, I want you to visit them. Like if you're at 2, you need to visit 2, 1 first, 2, 3, 2, 6, because I want them by the order. So who can tell me how are you going to input them now in the stack? Because in this question, I told you follow this, a JCC list. If you go to the 2, you have to input 2, 1 first. But now I'm telling you, don't follow this. I want you to be able to visit these to go to 2, 1 first. Not here, you went to 2, 6 first. Okay. Think about it a bit more. Yes.
You put the biggest number first in the stack, so that the last one in the stack is going to be the smallest one.
Very good. We've done this before, guys. We've done this before, I think, in maybe binary search yours in one of the courses. We said the stack is always whatever on the top is going to go out first. So if I have for me 2, 1, 2, 3, 2, 6, and I want to visit 2, 1 first, which one should be on top? 2, 1. That means I need to input 2, 6, 2, 3, 2, 1 to be able to visit them in the right order. So be careful. Read the question, the assignment, and the exam. Read them careful. Now, with a bit of more training that we're going to see in next sessions, in the exam, you don't have to do the stack. For me, I'm going to ask you, for example, visit the DFS without a stack, like visit. It's up to you if you want to do a stack on the side or not, that's up to you. But you don't have to show me, for example. Some of you are going to look at it, they're going to say, oh, you know what, 2, 1, and then 1, 3. And then, for example, it's going to be 3, 6, 6, 4. Going to look at it, you're going to be able to do. Okay? Yes, sir.
Does it matter how we write the adjacent the list? Do we need to follow
Here you always follow the order.
right?
Yeah. Here in this case, if I don't give you any instructions, you always follow the order. Very good. So we're going to jump now to the BFS, because BFS is also a bit kind of. Okay. I want to put that on. Now, BFS, there's 2 ways that I may ask you to do it. It's either I'm going to tell you, do the queue. If I tell you do the queue, you have to actually do this queue and show me the queue. But sometimes, again, I'm going to tell you, do the BFS and give me the results. It's going to be up to you to do whatever thing that's comfortable for you. So what is the difference between BFS and DFS? We're going to do the same exact thing, but using a queue. So again, the steps are going to be the same. I have to in-queue something and then dequeue instead of push and pop. That's the only difference. In this case, we have the front of the queue here, the back here. You can flip it. Don't ask me why the front is on the right. Okay. So simulate breadth first search using the algorithm that uses the queue starting from vertex 3. So I'm telling you to start from here. I'm telling you to start from 3. Okay, guys? Okay. Now, again, I may ask you to do the adjacency list. Based on this, you have to be careful for these things. So, for example, 3 is what? It's connected to 3, 1, 3, 4, but also there is 3, 5 here, and 3, 8. Okay, so let's just not waste time on it. And we have it like this. Okay, so that's my adjacency list. Again, here, I'm telling you to just follow the order of the adjacency list. So what would be the first thing? You're at 3. Ralph, you had your hand raised a couple of hours ago.
Yeah.
Let's do it together. It's okay. So the same steps that we've learned. So what do you need to do? You're at 3. So what are you going to do?
We'll just put in the queue the edges of 3.
First, I'm going to put, for example, the visit. So let's go to this one. So we'll do the first one. Let's assume. So I have 3 here. I visited 3. And then also I'm going to put 3, 1, 3, 4, 3, 5, 3, 8. So how do I put them in the queue? Is from the back. So 3, 1, 3, 4, 3, 5, 3, 8. But when I want to dequeue, I'm going to dequeue 3, 1 first. Correct? Okay, very good. In this case here in the queue, even if you're following this adjacency list, it's going to be in the order from 3, 1, correct? Because it's not like the stack on top. So that means, what is the next step, Ralph?
Now we'll in queue.
We already in-queued them for you. So want to dequeue now.
Yes, sorry. We'll dequeue 3, 1 and visit the edge 1.
Very good. So you're here, that's 3. The first step, I dequeued 3, 1. So that means I have to visit 1. So I'll add 1 here. What else? How do I visit it? How do I visit 1?
Now we'll put all the edges of 1.
First, so I visit here. I have to put 3, 1 as the discovered edge, because how are you going to visit a node? Through an edge. So that's 3, 1. So what's next? The third step.
Then we'll visit all the other edges from 1. Or not visit.
Not in-queue all the edges. So I go here, that's 1. I need to put 1, 2, 1, 3, 1, 4. So how do I do that? Do I put 1, 2?
Yes.
Okay, so that's 1, 2. 1, 3, there's no need. 1, 4. 1, 5. And then 1, 6. And then 1, 8. Good? Very good. So we're going to do this whole row. So let's start. Who's next to you? Oh, Melanie. Okay.
GQ. So we get 3, 4.
Group 4 here. So that's 4. And then how did we get to 4? That's 3, 4. So what's the next step after that? What's the next step?
Go and we in-queue all the edges of 4.
Very good. So we just put, now we go here. I have to put 4, 1, 4, 3, 4, 5, 4, 6, 4, 8. What's going to happen? So I'll put 4, 1. And then 4, 3. Do I have any 4, 3 here? Yes. Right? So 3, 4. I'm not going to put it again. And then 4, 5. 4, 6, and 4, 8. Very good. Very good. Yes. Oh, you have very good. That's a good catch. We already have. We don't want to push. Okay, very good, guys. So, who wants to practice? Who wants to do it? Who's the Fida?
Now we became 3, 5. Where's what 5 on
In the visited nodes, and then also have 3, 5. And then, yeah, we don't touch 3, 8. So 3, 5, I put 3, 5 only. 3, 8, I don't touch it because I'm working with this one, right? So I put 5 here, I put 3, 5 here, and then I go and I look at the edges connected to 5.
So we have 3, 1. We already visited. 4 we already visited.
No, where are you? Where are the 3, 1? No. So let's do it step by step. So 3, 5. I DQ'd 3, 5. I put 5 here in the nodes because that's 5. So I visited 5. How did I visit 5? 3, 5. So that's 3, 5. The third step, I look at 5. What are the edges connected to 5 so I can InQ them? So I go here. So I have 5, 1, 5, 2, 5, 3. I'm going to look. Is 5, 1 exists here? Where is it? Yes, so it's already here. I don't have to put it. And then 5, 2. No. 5, 3. We don't have 5, 3, right? Oh, it's already done. Yes. And then 5, 4. Do we have 4, 5? Yes, we have it here. 5, 6. By the way, these 4, 5, and 5, 6 that I'm doing, you can actually insert them again and take them from the queue because you only need to look at here. But now I think you're getting the point, so there's no need to fill the whole queue. Okay? But you actually can put them in the queue and then dequeue them. That's fine. Yes.
How do you know that we don't have to add 5, 1? Do we have to iterate over the queue or?
So technically here, it's just paper and pen. That's why I'm saying. So technically in the algorithm, you only look at this. That's what I was just saying for everyone. So you want to look here and you're going to insert it in the queue, but then you're going to take it off. So from an algorithmic perspective, you're going to actually insert them in the queue. But in the exam, if you have a very large thing, so you don't waste time, you can skip it if you know it. Okay, from an algorithmic perspective, you have to insert them. Yes.
So like,
But that's a very, I love this comment here. If you're thinking from an algorithmic perspective, that's amazing comment, because if I have to look at the queue, it's off n for me, for example. Correct? So it's you're destroying the whole time complex algorithm. So that means data structure worked for you. Very good. But here we're just talking how to solve it in paper. Yes.
so do 41 and 41 become back edge?
So when we arrive to them, we're going to.
We didn't put them in the list anymore.
Mm.
Because they were already, they weren't discovered edges.
Okay. I know what you mean. So technically, at some point, we're going to need them to put them in the cross edges. So it's better to keep them in the queue. Yes. So we don't end up with this. Okay. So let's keep it. So let's keep it this way. So let's keep them in the queue. Just also because other than the algorithmic, we need to use them for the. So let's do it in a cleaner way. So we said that's 1, 8, 41, 4, 5. So we were doing which one? This one, right? Okay, so we inserted everything, 5, 1, 5, 4, and everything. We left them in the queue. So what happened now, guys? I'm going to continue with the 3, 8. If I want to continue with 3, 8, what should we do? 3, 8. I'll pop 3, 8. Is 3, 8 visited? No. How am I going to visit 3, 8? That's the 3, 8 here. And then I'm going to go to the 8, and I'll find what? I have to put the 8, 1, 8, 3, 8, 4, and everything here. So if you look here, so we put 8, 1, 8, 4, 8, 5, 8, 6, 8, 9, and we 8, 9, and we added the 3, 8 here. So good? Good so far? Okay, now 1, 2. The same thing. 2 is not visited. So I'm going to if I pop 1, 2, 2 is here, and then 1, 2 is here. Where I'm going to put 1, 2, 1, 2. Correct? And what's next? All the edges of 2.
1, 2, 5, 2, 6.
Exactly. So what's going to happen? I'm going to have this 2, 5, 2, 6, 2, 7, 2, 9. Who's confused till now? Anyone? Any question? Anything? Very good. 1, 4. 1, 4 is 4 visited. It is visited. So now we're going to use this 1, 4 to have it where at the cross edge. So you see that's a very good comment also that no, we shouldn't skip them. Let's keep them in the queue so we can be able to put them in the cross edge. Good? Okay. 1, 5, what's going to happen to the 1, 5? 5 is the 5 visited. Cross edge again. Very good. So I'm going to take this and put 1, 5 here. And 5 is visited, so I don't need to enqueue anything from 5. So 1, 6. Is the 6 visited? No. So now 6 is not visited. I'm going to do 6 here, 1, 6 here. And what's next? I'll go to the 6 and enqueue everything related. So who's still confused about this procedure? Yes. Yes.
Point of separating discovered edges and crop.
So one of the main things for a BFS and DFS, one of the roles or goals is to find if we have a spanning tree. What did we say? What is a spanning tree? Spanning tree is when you visit all the nodes, but you don't have a cycle. So if you don't have any back edges, what does it mean? You don't have a cycle. If you have one back edge, that means there's a cycle here. So you need them. Why? Because who can tell me, okay, let's answer this question. Let's go back now to the, it seems like you like the idea of connecting things. So let's go back to the algorithm and time complexity. Why it's beneficial? We said, okay, cross edge, we're going to keep them. So we'll be able to find if we have a cycle or not. If we don't keep them, can we find if we have a cycle or not? Yes, you have to traverse again. So what are you saving here? If you're saving them, it's going to take you off 1 to know if there's a cycle or not. But if you're not saving them and you already did the traversal, it already took you off M. So why not benefit from this time that you traversed and keep them? So whenever you needed to go there. If you don't keep them, each time you want to find if there is a cycle, you have to traverse. So that's how we think from a time complexity perspective from all of these kind of things. Okay, guys? Very good. I've been teaching this, like this maybe the 4th or the 5th time that I've been teaching data structure. That is the first time that the students actually ask me questions related to the main idea. So I'm very happy. Usually they only focus, okay, in the exam, would you give this us or would you say this? So at least that's good. Very good. So 6, I'm going to enqueue the 6. Okay, very good. Now 1, 8. Is 8 visited? Yes. What's going to happen? Where I'm going to put the 1, 8 in the cross edge. Do we all understand why it's on the cross edge? Because it's visited. So I'm going to put it in the cross edge. Now, 4, 1. Is 1 visited? Yes. So 4, 1 is in the cross edge. And you can see whenever I add something to the cross edge, I don't do any enqueues. 5, is 5 visited? Yes, 5 is visited. So everything is going to be in the cross edge. Is 6 visited? Yes, cross edge. Is 8 visited? Yes. 1, yes. 2, yes. 4, yes, it's visited. 6, yes, it's visited. 8 is visited. 9 is visited. Do you see these? So please, you can either, I think these are, no, each one is on the page. So even if you're using the PDF, you can see the steps. Some of them, guys, like the AVL tutorial, it's better to download it as a PowerPoint and go through the animation. It will help you a lot to figure out how to go to the Z, Y, X, because if you see it like they are all on the same page, you're not going to be able to figure it out. But do the animation, it will help you. So 1, 4, 5, 6. So everything here at this point is visited. So we just visit 9, 6, 7 is not visited. You see, guys. So here I'm popping 7. Is 7 visited? No. What I'm going to do, I'll add 2 7 here, and then 7 here, and then I'll go to 7, and then add NQ all the edges of 7. 2 9 visited. I think everything else is visited. Now you're done. So you ended up with this. Now, this will take lots of time sometimes. So it's a queue. That's actually what's happening if you're writing your program and anything. Now, what about, I ask you guys, and yes.
What situation is it better to use a queue instead of a stack?
I think you'll figure it out. Think about it a bit. What are we solving? BFS. Very good. BFS is connected to what? In the WOO clap, what did we say? BFS connect to Q. BFS stack. Always. So for example, whenever BFS, you don't have to guess. It's a stack. It's always a queue. DFS, always a stack. Now, even from a logical perspective, what did we say? A stack is always last in, first out. So if you're doing depth first search, you're always going deep and deep. You're going to need this this criteria of last in, first out. And the queue, no. The queue, it's based on levels. So this takes us to the levels. Yes.
Who knows the short path?
The short path usually, I think it's based on, I have to give you the 2 nodes. I have to give you, for example, 3 and 2. And then if you follow these, like the edges, you're going to find it automatically. And so it's going to be, if you do the breadth first search, you're always going to end up with this. I think in the slides, we have the algorithm for the shortest path at the end of the slides.
It's very simple.
So guys, here I want now to talk about something important that I think it's asked from you in the assignment and also in the finals. We always said BFS, it's based on levels. So where are the levels here? And we say BFS is like usually level 0, level 2, level 1, level. Where are the levels? So how can we figure out the levels here? So look at them. The shortcut to do this is very simple. If you understand the shortcut, you always do this correct. Guys, you're starting from 3. So 3 always is L0. The one that you're starting from is always the first level, because that's the one that you're going to visit first and add the InQ first. Now, what is level 1? Always remember, it is the nodes that are connected with only one edge with the first node. So if the only thing that separates you is one edge, that means that's the next level. Each level will add one extra edge from where you're starting. So for example, how many edges do I have between 3 and 2? I have 3, 1, 1, 2 to be able to get from 3 to 2, correct? Is it one edge or 2 edge? How can I get from 3 to 2? Can I jump 3, 1, 1, 2, 2 edges? So that means 2 is not from the, yes, Ra.
You have to pick the shortest amount of edges, because we can also get to 2 in different ways, no?
No, that's because it's levels. That's the whole idea. So it's shortest thing. So in the slides, I'll put the slides also now to remind you. So in the slides, so that's even the algorithm is working like this. If you remember, inside the algorithm, we're creating a list each time. We're saying, okay, this is L0, Li technically. And then when you're done from this, I plus 1. So that's L1, put these. So it's like we're creating L. So if you want to think about it, look at this. So here, for example, It's not related to what we're talking, but here in this big queue, it can be more than one queue connected to each other, right? So the L0, L1, L2, these are lists, but each one is also treated as a queue. So we're saying, so let me draw this for you first. So I'll take you to a much simpler one. So this one is a bit complicated. So let's go to a simpler. If we go down here to this one. This is simpler. So look at it. It's like this. So that's my L0. Okay. Usually, what's happening? This is my L1. When you're visiting from the breadth first search, what is the idea here? This is your first queue, for example. There's only one thing. So you have two. You go here. You pop like two, you DQ two, and then you moved on. Now you have another queue of 1, 3, 6. So you're going to do 1 first. It will take you to, for example, also give you 4. But where are you going? Because it's a queue, where are you going to put the 4, for example, here? So you have to finish 1, 3, 6, and then you go to the next level. So that's the idea. It's like level by level. So breadth first search is literally level by level. But we're using the queue, which combines all the levels together. But if you look at it in the algorithm, each recursive call, for example, or whatever you want to name it, is treating this L1 as the first queue. You're done, you're jumping to L2 as the second queue. So in this case here, but now, if you're looking at it without an algorithm in the exam and you want to find this out, by the way, in the exam, and I think in the assignment, maybe we already did this or something. In the exam, usually we give you the algorithm at the end. Just in case you're not able to remember, you can look at the algorithm and figure it out from the algorithm. But I'm teaching you something that is much easier than looking at the algorithm in the exam to figure it out. But the algorithm is with you in the exam. You can look at it and you'll be able to find it. So again, guys, the way that you want to do it, LZ, you started from 2, so that's L0. The nodes that are connected with one edge with you are this, 1, 3, 6. So one edge. So that's L1. L2 will be what? So 1, 2, right? And then even here, 1, 2 you have. So that's only L2. This 5 is going to be what? 1, 2, 3. That's L3. As simple as that. Okay? It's very simple. I think we're done, right? Okay, so there is still another question. Is this one? But it's in the tutorial, so you can look at it. This one, guys, just to give you a heads up, this one is not using the queue. So don't get confused. So when you see it here, you'll see a queue for you. But here, I'm just asking you to do it yourself without a queue. So you can do it based on the levels. So you can skip steps. The steps that we're putting all the time inside the queue, you can skip them. What I want is at the end to have it, for example, draw it like this. That's what I need at the end. But you can do a queue if you want or not. Okay? Good?